So, on the board, we have some announcements. Vocab 9 is due tomorrow. Some of you have already gotten that done, so I thank you for that. I've also posted Prepare to Learn 9A, due tomorrow night as well. What do you need?
Is it okay if I cut it after class? I couldn't find any scissors.
Yeah, there's scissors over there in one of those white baskets. Okay, so those are due tomorrow night. Then there are 2 active chemistry assignments that I have posted. We will get to about half the content of the first one today. And then you should be able to do homework 16 today, but it's pretty calculation intensive, so I'm gonna give you a little extra time for that. So they are due Sunday and Tuesday. Extra credits, if you have your extra credits, that for the stuff to prepare you for the test on Monday, you can bring it up here. Then there are 2 events this week. This is National Chemistry Week, and it is National Chemistry Week because tomorrow is Mole Day. So Mole Day is 1023 because Avogadro's number is 6.02 times 10 to the 23rd. And so tonight we have a webinar. There will be door prizes and scratch and sniff stickers and spiced beverages and trivia and a webinar. And usually they're pretty good about targeting their webinar to a general audience rather than specifically scientists. So it should be interesting. So we'll get started around 6:30 and then should be wrapped up by 8 o'clock. So that is worth 5 extra credit points because all you have to do is show up. Saturday for 10 extra credit points. You can volunteer for an hour at the library. Public library, if you know where CVS is, it's behind the CVS. The CVS, if you go take Broadway down towards Lexington, you'll see the CVS on the way down there. It's not even a mile from campus. And so if you want to be involved in that and need a ride, just let me know. Usually there are plenty of people who have cars and I can get you connected with somebody who has a car. So I will need people at like 10:45 to kind of help me set up. And then stay for an hour, people in the middle, and then people to stay until 1 and a little after to help me put everything together. We usually just like throw everything in boxes and stuff them in my car, and it takes less than 15 minutes to do it. So questions about any of that? A lot there.
Tonight's in the library.
Say that again.
Tonight is in the library.
No, Saturday is the library. Tonight is here in 212. Yeah, the big lecture hall, and it's on the board over there. All right, any other questions? Okay, so we are not going to chapter 5 now. We are going to chapter 9. This is because our old textbook, chapter 5, was gases, and we didn't want to change around the labs. And so, we're doing something a little out of sequence. It does make a little more sense to do gases here because we're going to throw in some stoichiometry with gases as well. And then the chapter 5 will be energy. So let's get started talking about gases. One of our 3 domains is the particulate domain, that the molecules are far apart. And this has a couple of consequences that are relevant. One of them is that the molecules are so far apart that if they have attractive forces, like if they're polar, they can't really feel that. So if one molecule is here and one molecule's over here, and there would be an attraction between them, the distance is so great, they really can't feel that. It, sort of like if you're looking from one end zone to the other, you can't tell how attractive the person on the other end of the end zone is. That's just too far away. So because of that, no matter what the particle is like, if it's big or small, if it is something that has strong attractive forces or no attractive forces, they all kind of behave the same. So we call those ideal gases, that they're all behaving the same. Now that's true under ambient conditions, the kind of normal, kind of temperatures that we live in and air pressures that we live in. The story changes if we make some extremes, and we'll get to that probably next week. But under most conditions, ideal pressure is pretty typical. Ideal gases is pretty much the name of the game. The other consequence is that because they're so far apart, they tend to fill up their containers. So if it is not like in something that's used for measuring, it can be hard to tell what the volume is. Like, what is the volume of gas in this room? We'd have to know the size of the room, but we'd also have to take out the volume of the chairs and the desks and the people and all of that stuff. Even if I have like a 500 milliliter flask, I might have a mark on it that says 500 milliliters, but then there's space above that. And so it's kind of hard to tell. So we have to sometimes use special equipment, and we'll look at some of that to tell the volume. To make it easier to measure the gases, we sometimes look at pressure because it's a lot easier in some ways to measure the pressure than it is to measure the volume. Okay, so in talking about gases, there are three main things that we look at: the temperature, the volume, and the pressure. So while we might be concerned about the temperature and the volume and the mass of a solution or of a solid, we don't usually look at the pressure of those things. All right, so how do we measure pressure? Pressure is exerted pretty much the same in all directions. So the pressure down is the same as the pressure to the sides, it's the same as the pressure up. And we have lots of different kinds of equipment that can measure pressure. You have probably seen references to pressure in a variety of ways. So for example, you've probably seen a weather map. The H stands for high pressure, the L stands for low pressure. For reasons we'll go into later, whenever there is a high pressure area, that usually means sunny weather, very few clouds. So you can see on this map, very near Kentucky, we have a high pressure area. And so it's probably a sunny day in that area. Where there is low pressure, there tends to be poorer weather, and it kind of depends on how much the temperature is changing and how much moisture is in the air. But you could have something as simple as clouds or more wind, or you could have something like storms coming through. The blue lines with the blue triangles are showing what's called a cold front. So that means that the air on one side is several degrees cooler than the air on the other side. If it's a big difference, that's where you get like storms. If it is a very small difference, then maybe it's just a little more breezy. And then the red ones have the circles rather than the triangles, half circles. Those are warm fronts, so it's the opposite. The air coming in is warmer. I happen to pick for this picture a map that has a lot of stationary fronts, and that's where you see both the blue and the red, so kind of going from Oklahoma up to Chicago there. That's a stationary front. And that just means that whatever that weather is, it's going to stay the same for a while because there's nothing really pushing from one way to the other. As a general rule, in North America, our weather tends to move counterclockwise. So what this means is if we look at this low pressure area near Texas where there's the cold front, it's kind of moving down and a little bit to the right. Whereas up in Canada, we can't see the half circles, but the low pressure areas up there have them moving more towards the left. So in this part of the country, our weather generally comes from the west and moves towards the east. So the weather we're having today might be what's going on in Virginia in a day or two, depending on how fast that weather is moving. The reason it does that is because the air near the equator is very warm, and so it's going to expand. And it wants to move northward. And rather than moving all at once, it has to create kind of a circuit to make things keep moving. And so the circuit moves up the Atlantic across Canada, that's what it's called, and then down the Pacific and kind of forms a circle. And then there's a circle in the opposite direction that is next to it over including part of Europe. All right, this metal stick here, anybody know what that is? It kind of looks like a thermometer. It does measure pressure. Yeah, it's a pressure gauge, particularly for tires. So car tires and bicycle tires have like a little knob that you can put the air in. So you take this part that has the red circle and put that over the knob to release just a little spurt of air. And that spurt of air is going to shoot this white plastic stick out of the back. So it might be hard for you to see, but that stick has little lines and numbers on it. And depending on how far it moved out, that tells you how much the air pressure was. So that's a cheap way to measure air pressure that doesn't involve computers or anything like that. Most people would prefer something that a little simpler to use. So, you know, there are definitely other devices that are less cheap that you can do that with. If you have a bicycle, you've probably seen a bicycle pump like this. A lot of times the bicycle pump will have attached to it a little circle that tells the pressure there. And if you've looked at that, the pressure on that is probably going to be in PSI, pounds per square inch. And that's so that you don't overinflate the tire and burst the tire from the inside. Okay, so what happens with pressure? Well, we can think of a pressure as a push. If we had two people pushing against each other, if one was pushing harder than the other, they would move in the direction that the one that was pushing harder was moving. And pressures are kind of like that too. If you have a flexible boundary between them, then you end up with some movement. So when the pressure on two sides of a material are different, the material will tend to move. If it's flexible. So if we have something like a window, if we had, instead of the solid glass, we had that made out of like a plastic sheeting, then if there were high pressure outside, it would push that sheeting in. If it was lower pressure outside, it would push the sheeting out. It's a motion. It's going to keep moving until either it equalizes that pressure or we have some kind of either a breakage so that they join together, or the constricting forces of the material cause that to stop moving. So, you know, if the sheeting just can't move anymore, but the difference in pressure isn't great enough to break it, it might stop. All right, so what we are looking at here are simple variations on what's called a barometer. And so we have the pressure of the air on the outside. This blue line, very pale blue line here, is showing the air is pushing down on the liquid in that container. And so as it pushes down, it's trying to force the liquid up into the tube. Now that tube is a little bit like this tube. We'll talk about this tube more in a minute, but this tube is closed at the top and there's no air up there. It's a vacuum. And so if we could zoom into the air on a particulate level out here, we would see nitrogen and oxygen and all that, but inside the tube, there would be nothing, okay? So there's a limit on how much that vacuum can support the water on the inside, or whatever the liquid happens to be. So for water, we can push that water up under normal conditions about 34 feet. And then if we had a tube any bigger than 34 feet, we would start seeing that gap of a vacuum in there. If I have a denser liquid, then that height is smaller because we've got gravity from the liquid pushing down. If it's denser, there's more mass pushing down. So mercury, which is a silver metal, is about 13 times as dense as water. And so the height that water can go is about 13 times the height that mercury can go. So this is 760 millimeters, which is about 76 centimeters. So this is a meter stick, about 1 yard. That is 100 centimeters. And we said 76 centimeters. So this green stripe here is the 76 mark. So this is something that I could keep in a room, whereas 40 feet, I couldn't keep that in a room. That would be hard for us to look at. And so we can measure the air pressure by looking at how high mercury is pushed into a tube similar to this, with a vacuum at the top, and we can keep that in a room. And so we have one of those in one of the labs, not the Gen Chem lab, it's across the hall. And when you do your gas law labs for the next couple of weeks, you'll go over there and you'll look at that to determine what the air pressure is. So because of that, one of the units that we use for pressure is millimeters of mercury. It's literally just how many millimeters high we can move. So, as I said, that's called a barometer. The guy that came up with this measurement, and my apologies to anybody who actually speaks Italian, his name was something along the lines of Torricelli. And so we also use the unit torr. It is exactly the same thing as millimeters of mercury. It's just a lot fewer syllables. So I will usually say torr, but you will often see millimeters of mercury. You just have to remember they're the same thing. All right, so we normally like working with numbers that are between 1 and 10. So working with things that could be 750 and 740 and 770, we don't like that. So somebody a couple hundred years ago came up with the idea that why don't we call normal air pressure 1 and then just scale everything to that. So that's was originally defined as what the pressure is at sea level, because pressure changes as you change altitude. But even at sea level, we saw because of weather changes, we can have the pressure go up and down. So in recent years, it has been defined relative to millimeters of mercury. We'll look at that on the next slide. Other units you might see sometimes, PSI, that stands for pounds per square inch. Bar is a metric unit. Dr. Hamilton would love it if we always used bar. Pascals is the official metric unit. So the relationship between them is similar to the relationship between a milliliter and a liter, but instead of multiplying by 1,000, it's 100,000. So we don't call it a kilopascal because it's really 100 kilopascal. We just have a different number, bar. All right, so the only ones you are responsible for are the millimeters of mercury, atmospheres, and bars. You'll see the others in reference to pressure, but I won't ask those won't appear on tests that I have. All right, so the relationship between 1 atmosphere and millimeters of mercury is they defined 1 atmosphere as 760.0 millimeters of mercury. Now we have trouble with our weak little eyes seeing with much more precision than that. So we only get 4 sig figs on millimeters of mercury. So whenever we do a conversion involving atmospheres to mercury, that's a 4 sig fig change. And so the conversion is really just to take our pressure that is in millimeters of mercury and divide by 760, and that's going to give us our pressure in atmospheres. So, as an example, we mentioned that the higher up we go, the pressure changes. It's going to get lower as we move higher up. And so the highest place we can go and still be on land is Mount Everest. And on a particularly stormy day, it might have a pressure of 253 millimeters of mercury. So how do we convert that to atmospheres? So we set it up like this, and I encourage you to pull out your calculator. And I do have some calculators up here if you want to use one of mine. Say again. Yeah, so about 0.33. I got 0.333 when I did it, but you know, that was when I made this slide a couple of years ago. So was it 0.332 like 6 or something like that?
It's 0.363.
Yeah, so we would round it to 0.333. Okay, and the reason I did 3 sig figs is because I have 3 sig figs on the 253. Okay, what if I want to use bar? So it turns out a bar is pretty close to an atmosphere. It's 750 instead of 760. For some reason, we get 5 units on the conversion. I don't know who made the decision. I would have trouble seeing a difference of 0.06, but there you have it. So if I wanted to go from millimeters of mercury to bar, I would divide by 750 instead of 760. If I want to go from atmospheres to bar, I'm going to multiply by 1.03. I'm sorry, 1.013. The other thing you can do, I find it easier to do it this way, is that I can divide first by the 760 and then multiply by the 750 in order to, or I can divide by the 750 and multiply by the 760 rather than remembering the 1.01. You will need to memorize the 760. I will provide you the bar. But the 760 is something you should be using often enough in calculations that you should know it. Okay, so if I want to convert it, I could start at atmospheres that we already have, the 0.333, and I could multiply by the 1.013 bar, or I could say, well, I already know it in millimeters of mercury, so I could start there and divide by the 750. So do one of those. Plug that into your calculators. See what you get. It should be close to the same number because 1.01 is pretty close to 1, but it's going to be a little bit more. So I get 0.337. See if you nods out there. Looks like that's what you're getting. Okay. So let's think about how we might measure these things in lab. You're going to have two labs that involve the gas laws. You will have a setup somewhat like this. It's not going to involve flasks though. So you will have the container at the bottom here is what we call a crystallization dish. And that's so that we can have water, but also lift up something so that the water can flow freely in and out and not just get stopped. And then you're going to collect the gas. Instead of in a flask, you're going to collect it in this tube that kind of looks like a burette. It even has the 0 at the top here and it goes down to 50, just like a burette does. But a burette has that little nozzle at the end. This doesn't have that, it's just open. And this is closed at the top, okay? So as the bubbles form and they go to the top, we can measure the volume of the gas from the top, okay? That's a lot easier than using a flask. And because this is so narrow, we can get pretty precise measurements of a volume. So the first week, you're actually going to be doing the reaction in the bottom of this. You'll have like a coil of magnesium that you'll stick in here and it'll just react and form bubbles up here. So there won't really be anything else. In the second week, instead of attaching it to a flask, I think we use smaller amounts. So we use a test tube with a hose connecting them. All right, so what we do is we don't have anything on the inside of this. This is really narrow. We don't have anything in there that's measuring the pressure of this gas. So what you're going to do is you're going to measure the pressure of the room. And for lab, we assume that those two pressures are the same. But remember that when there's a difference in pressure, we're going to have a difference in height. And that's what happens is we're going to have some of the liquid somewhere in our eudiometer. That's what this is called, is a eudiometer. And then it's going to be lower on the outside. So what we used to do is have you take the eudiometer over to the sink. And we have a big bucket of water and you could stick it in there and get it so that it was right height. But we found that by the time people were moving around and sloshing water and moving their finger and letting out water, that we ended up having more mistakes from all of that moving around than we get from the difference between what that pressure is and the air pressure. So the long and the short of it is the error that you make from trying to make the correction is greater than the error that exists because they're not exactly equal. So we just assume they're equal. Okay, so technically the water level should be equal, but we don't do it that way. All right. So we measure the properties of pressure, volume, and temperature because they correspond to things that are happening with the particles, which are normally molecules. So sometimes I'll just say molecules, but it could be atoms if we're dealing with a noble gas. So obviously the volume is just like how big the container is, how spread out are the particles, and that's determined by how big the container is. I can't have a negative volume. Okay, so our units must be positive. We can't have any negative to them. And there's no such thing as a negative volume, so that works. What does pressure measures? It measures how many collisions we're having, how frequently the molecules of the gas are interacting with the container. So we can't have a negative number of collisions, right? So there's no negative pressure. Technically, it is also including how massive the particles are and how hard the collision is. But for any one given gas, that doesn't change. And so we're just going to simplify it and say it's the number of collisions. Okay, so pressure is measuring how many collisions there are. When there's 0 collisions, there's 0 pressure. When there's more collisions, if we double the collisions, we double the pressure. What about temperature? Temperature is a measure of kinetic energy. So if you've ever had physics, you might have seen this formula before. KE, or kinetic energy, is 1/2 mv squared. Now don't worry, we're not going to really be looking at this V much, so we're not going to confuse it with volume. For your purposes, V is volume. But what this is saying is the kinetic energy of something is dependent on the mass of that thing and how fast it is going. So a car that is moving at 100 miles an hour has more kinetic energy than a car moving at 10 miles an hour. So if you get hit by a car going 10 miles an hour, it's going to hurt. But if you get hit by a car going 100 miles an hour, you're probably going to be dead. So we have a difference in energy based on that difference in speed. So what that means is that the slower the molecules are going, the lower the temperature. And when we have no motion, they're not moving at all, then what's the temperature? Should be 0, right? We need something that scales with that motion. Unfortunately, we do have temperature scales that go negative. So Celsius and Fahrenheit don't really measure this very well. We need a different temperature scale that is absolute, where the 0 actually means 0 motion. Okay, so the property should scale according to that. When we double the velocity squared, when we double that kinetic energy, we should also double the temperature. But if I have something at 1 degree Celsius and move to 2 degrees Celsius, that's not really doubling the kinetic energy. So I need a different scale. So what this means is that for gases, our temperature will always be in Kelvin. This entire chapter, everything has to be in Kelvin. Okay. So Kelvin, the size of a Kelvin, same as the size of a degree Celsius. So if I increase by 10 degrees Celsius, I also increase by 10 degree Kelvin. So these two thermometers show the scales relative to one another. What happens at 0 degrees Celsius? Why is that significant? It's the freezing point of water. So it's significant for water, but it's not really significant for any other chemical. So this was kind of an arbitrary scale. So what they decided is, based on measurements actually using gases, they figured out, okay, what would the lowest possible temperature be? And they figured out in Celsius that lowest possible temperature is this. Now, this image came from a European book or something. In Europe, some countries use a comma instead of a decimal point. So this is actually the decimal point, not a comma. Okay. So this is 273.16. And most textbooks you'll see 0.15. I guess the next digit is one of those where it's probably like 0.155 and they rounded to 0.16. We usually round to 0.15. I don't care because we don't usually use that digit. We usually only go to the tens place. Okay, so we will have to change temperature. The way you change temperature is whatever it is in Celsius, you're going to add 273. So if it's 0 degrees Celsius, we add 273. Room temperature is 25 degrees. So 25 plus 273 is 298. Okay, so most of the temperatures that you deal with are going to be between 273 and like 310. We don't really get outside that range in our labs.